For this lesson, we're going to actually look at how these exponential functions can model real-life problems. So we've got the two scenarios. We've got exponential growth or exponential decay. First, we're going to look at exponential growth, and it doesn't matter actually whether you have growth or decay. Both can be modeled by this function. Okay, y equals a b to the x. Remember, the a is that initial value or your y-intercept. The b is the rate at which you are growing. It's your growth factor. So b is always starting at 100%. And when you have growth, you're adding the percent it's growing by. And then, of course, you change those into decimals. So 100% really is a 1. And then your other percent that you're going to be growing by would be that percent over 100. So you would take your percent, that's supposed to be the percent, and then divide it by 100 to change it to its decimal form. So, a small town in northern Ontario called Decimal Point had a population of 1,000 in 1980. Its population has been growing at a rate of 0.2% per year. So, we know initially we have a population of 1,000. So, our A value is 1,000. So, we're going to set up a model. We're going to use P instead of Y. So, our population would be equal to AB to the exponent M. So M represents the number of years after 1980. What we need to get is our growth factor here. So I'm just going to write this down as a separate step just so you can understand hopefully what's going on here. So our growth factor is always starting at 100%, and then we're going to add the percent we're growing by. So 100% plus, and then we're growing by 0.2%. And now we're going to change those to the decimal forms. 100% is just one whole. And then 0.2 divided by 100 is 0.002. And then when we add those together, we get 1.002. Now you could do it the other way. I'm just going to put an option here. From that step, you could add those together and say I have 100.2%, and then take that number and divide by 100. And you get 1.002. So use whichever method here makes sense for you. So now we're ready to start to write our equation. The population would equal the initial population times the growth factor to the exponent of m, and m is the number of years since 1980. So what is the population in 2020? We need to figure out how many years have passed since 1980. So we're going to take 2020 and subtract 1980 from that, and that gives us 40 years. So 40 years after 1980, so our M is equaling 40 here, and we're going to calculate the population then. So it's just a matter of putting this in your calculator. Now remember, BEDMAS says that you have to apply exponents before you do multiply. So you want to actually calculate this piece first. So in your calculator, put your base of 1.002 in to the exponent of 40, and then get that answer in times by 1,000. Some of your calculators will automatically do that for you in the correct order, but just be careful. When you do that, you should get 1,083.2, which you can't have 0.2 of a person, so we'll just say the population in 2020 is 1,083. All right, the next part, in what year? So now we need to figure out a value for M. In what year? So let's get the right tool out here. In what year? So this is the questioning of M. Does the population double itself? Double itself from 1980's population. So originally your population started at 1,000. If we double that, so initial population was 1,000, and if we double that, we get 2,000. So that's what the population value is. That's the P. So we're going to put 2,000 in for our population, and then we have our equation here of 1,000 times 1.002 to the m. Now to solve, the first step of solving is that we're going to divide both sides by 1,000 to undo the multiply, and that gives us a 2 on the left side of that equal sign. So 2 is equal to 1.002 2 to the m. Now at this point, the only way we can solve for the m is if we do a guess and check. Okay, so there are some ways to solve it using logarithms. However, we don't have time for that, and actually it's not even part of this course. We do that in grade 12. So by guess and check, if I let m equal 350, I got about 2.01. So let me just move this up a little bit. So guess and check, I did 1.002 to the 350, and I got about 2.01. So that's really close. So I could try 1.002 to the 345. I got 1.99. I've done this ahead of time if you're wondering how I'm getting this so fast. So then I just narrow in between 350 and 345. So 347 was what I came up with as being very, very close to exactly 2. Okay, so it did round, but so 347 years after 1980. So if we take 1980 and we add 1980 and we add 347, that takes us like way in the future. And I'm sure there's all kinds of things that can happen between now and then that would disrupt this model. Okay, so by the year 2327, the population will have grown to double its original size in 1980 following that particular pattern. Again, that's highly unlikely that the pattern is going to stay the same over that great span of time. So extrapolation doesn't always work all that well. A lab dish has an initial population of 10 bacteria. So we're starting with 10. So that's our A value here. If the population doubles every minute, what is its count at the 1 hour mark? Okay, so population is doubling every single minute. If you're doubling, you're increasing by 100%. So your growth factor would be your 100% plus your 100%, because you're adding itself to it. So your growth factor, or B, would be your 100% plus your 100%, which is 200%, which is just a 2. So anytime you see a base of 2, you're thinking you are doubling. Okay, your initial population is the 10, so then your population would be 10, 2 to the exponent n. And n would be your number of minutes. So n is number of minutes. So technically we should be defining what our variables are representing. Minutes. Oops, there we go. All right, so at the 1 hour mark, we need how many minutes that is. And hopefully you know at this point in your life that there are 60 minutes in an hour. So we're going to have 10 times 2 to the exponent 60. And then you just punch that into your calculator, and you're going to get, my calculator took it to scientific notation, and depends on how your display works, I get this as scientific notation, times 10 to the exponent 19. That really just means move that decimal 19 places to the right. The number's so big it wouldn't fit in the display screen. So hopefully you remember that from science class. All right, our next part here. How long does it take the population to reach 80 if it's doubling every minute? Again, we're going to use just a guess and check to solve for this, but we're going to take that population equation. So population equals 10, 2 to the n. We're going to put 80 in for the actual population. And, 80. Okay, the first thing we want to do is divide both sides by 10 to eliminate this 10 that's multiplying or keeping the n by itself. That gives us 8 equaling 2 to the exponent n. Now this one's actually kind of nice. You can try 2 to the 1, which is 2. 2 squared is 4, and then 2 cubed is 8. So the n, 2 cubed, equals 8. So therefore n equals 8. So therefore it takes 8 minutes for there to be 80 bacteria. Okay, this question's a little bit challenging. If the population's doubling every 30 minutes, so originally in part A, it was doubling every single minute. Now we're doubling every 30 minutes. So we want to look at how many groups of 30 we are going to actually have this doubling. How many bacteria will there be after 24 hours? So let's assume we're still starting with the 10 bacteria, as the question initially said. So our population starts with 10 bacteria. We're still doubling, so our growth factor is still 2, but we're doubling every 30 minutes. If M represents, or N, I should say, N is the number of minutes, we want to figure out how many bacteria there would be after 24 hours. We need to figure out a way to take our number of minutes and see how many groups of 30 we can get. Well, that's just division. So instead of using n as our exponent, which means we would be doubling every single minute, we're going to use n divided by 30 as our exponent here. So if we had 30 minutes, then when I divide it by 30, I get 1. So it's going to double it's only going to double once in that time. If I had 60 minutes and I divide that into groups of 30, then I'm doubling twice. If I had 120 minutes and I'm doubling every 30 minutes, it's actually doubling 4 times. So that's why my exponent now is an n divide by 30, because I want to take the number of minutes and divide them by 30 to get how many times it's actually doubling in that time frame. In 24 hours, we need to figure out how many minutes there are. So we're going to take 24 hours. Whoops, that's supposed to be a time sign there. Back her up. Times by 60 minutes for every single hour there. 24 times 60 gives us 1,440 minutes. So that means really we should be doubling 24 hours every half hour 48 times. So if we do 1,440 and divide it by 30, so divide that by 30, just check on the calculator. Sure enough, I get 48 times. All right, so that's how we can do that. And again, we're going to get scientific notation out of that. I got about 2.81 times 10 to the 15, which really means move that decimal 15 places to the right because it's a positive 15. All right, I'm going to, time-wise, I'm going to do a new video for the next part of this handout.